Curious, observant. Deep inside your bloodstream right now, a highly engineered, microscopic security network is on a constant, vigilant patrol. Your body employs billions of specialized units. Heavy-hitting macrophages act as garbage disposals, physically swallowing microscopic threats, while cytotoxic T cells operate as precision assassins, hunting down corrupted cells one by one. Yet, despite having one of the most sophisticated defense grids in nature, this system fails. For centuries, infectious diseases have consistently overwhelmed human biology, filling hospital wards and devastating populations. The sheer mechanical superiority of our immune system raises a difficult question. How do so many invaders manage to get past it? The answer lies in how we view the enemy. Pathogens are not passive targets waiting to be destroyed. Millions of years of evolution have turned them into highly specialized saboteurs, equipped with a specific playbook designed to bypass every security layer you possess. By decoding this playbook, analyzing exactly how these invaders hide, lie, and strike back, we can move beyond the limits of our natural immunity. Phase 1 is passive evasion. To survive long enough to replicate, a pathogen's first obstacle is the body's innate immune system, the fast-acting eat and destroy first responders. Normally, a macrophage swallows a pathogen, trapping it in an internal bubble called a phagosome. That bubble is then flooded with digestive enzymes, dissolving the invader. But pathogens have developed a tactic we can call the prison break. Looking at this medical text, we see exactly how specialized invaders, like the parasite Toxoplasma gondii, survive. Once inside the macrophage, they secrete chemicals blocking the phagosome from merging with the cell's stomach, turning a deadly trap into a safe house. Other invaders rely on physical armor. This diagram of a bacterial cell highlights the outer capsule layer, labeled K. This dense, slippery shield is essentially a biological force field. It prevents the immune system's floating proteins from latching on and punching holes through the bacteria. By blocking digestion or wearing slippery armor, these initial tactics blind our first responders. The infection takes root before the body's heavier, more intelligent defenses realize there is a breach. Once an infection spreads, it triggers phase 2, active deception. The pathogen now has to outsmart the adaptive immune system, a network that identifies specific enemies with surgical precision. Cells have a built-in alarm system called MHC1. Think of it as a chemical display tray. If a cell gets infected, it chops up a piece of the invader and places it on this tray on its surface, signaling patrolling T cells to destroy it. Certain viruses survive by blinding the guard. The virus actively dismantles the MHC1 tray inside the cell before it can reach the surface. When the T cell inspects the infected cell, the display is empty. The cell looks healthy, and the T cell floats right past it. Parasites like schistosoma opt for identity theft. As they navigate the bloodstream, they physically harvest host proteins and coat their own surfaces with them. The immune system scans the parasite, detects human proteins, and registers the invader as self. But the most elaborate deception is shape-shifting. Our immune system uses antibodies, Y-shaped proteins that lock onto a pathogen's specific surface shapes, acting like a highly accurate facial recognition system. Pathogens like the trypanosome parasite counter this by constantly changing their faces. This graph illustrates the resulting waves of infection. The host produces antibody A to fight the parasite, so it swaps surface proteins to type B. As antibody B rises, the parasite shifts to type C. The immune system remains one step behind. This chart maps the genetic mechanism that makes this possible. The parasite constantly splices new, silent genes into the active position, continuously overwriting its own surface glycoproteins to render previous antibodies entirely useless. Through these tactics, the pathogen turns our biology's intelligence-gathering mechanisms against itself, forcing the body into a war of constant, exhausting confusion. If stealth and deception fail, a pathogen moves to the climax of its playbook, Phase 3, direct sabotage. Here, the invader stops hiding and targets the immune system's command and control center. We can call this tactic assassination. The entire immune army is coordinated by the T helper cell, or CD4+. This cell acts as the biological general, issuing the chemical orders that mobilize the rest of the immune network. This diagram shows exactly how the human immunodeficiency virus, or HIV, bypasses the soldiers and goes straight for the general. The virus uses a specific surface protein called GP120 to dock perfectly into the CD4 receptor on the T helper cell's headquarters. Looking at the bottom of the diagram, we see the immediate consequence. The pathways to the B cells and killer T cells are crossed out. The communication network collapses. The soldiers are still there, fully armed, but without the T helper cell to issue orders, they remain inactive. By decapitating the leadership, the virus achieves total victory, disabling an entire immune army without having to fight a single foot soldier. The human body is the site of a billion-year arms race. As our immune system adapts, pathogens will inevitably evolve new methods of sabotage. Mapping these specific tactics, the prison breaks, the identity theft, the assassinations, allows us to reposition ourselves. We are taking the role of biological architects, using the enemy's own blueprints to fortify ourselves. We can now engineer targeted vaccines and synthetic immunotherapies designed to patch the exact breaches these pathogens exploit, fortifying the MHC1 display trays or stripping away bacterial armor. Mapping the enemy's strategy moves the battle from a struggle for survival to a contest of engineering. It gives us the tools to secure our defenses against a sabotage we finally understand.